Good morning, gentlemen, and welcome to the lecture presentation for chapter 14, which is oscillations. Yes, I know that we've skipped chapters 11 through 13. That is okay. It's even if we had been in school, we would have done the same thing. In any event, chapter 13 deals with oscillating motion, the motion back and forth. All right, whether it's up and down or left to right or whatever it is. An oscillation is basically just that. Things that oscillate include pendulums, like in a grandfather clock. Springs hanging with a mass will bounce up and down. That's an oscillatory motion. You even have oscillating fans in the summertime, where the whole head of the fan turns and then goes back. All right, that is an oscillation. So today we're going to start with section 14.1, which is equilibrium and oscillation. So let's start with a different kind of example. All right, let's say that we start with a marble that's free to roll inside a spherical bowl. So you've got a bowl sitting here. You put a marble on the very top, and you allow it to begin to roll. Well, it's going to go back and forth and back and forth. Past its equilibrium position. So a marble that's free to roll inside a spherical bowl has an equilibrium position at the bottom of the bowl. And eventually, because of friction and other things, it will come to rest there because that's the point where there's no net force on it. At any other location, the normal force and the weight are pointing in two different directions, and therefore you end up with a net force. For example, at this position right here, all right, the free body diagram shows the weight obviously going directly downward, but the normal force is perpendicular to the surface of the bowl at that point. And if you add these two forces together, you end up with a net force that looks something like this, or as drawn here. And that net force, of course, will draw the marble down toward the bottom of the bowl. Now, if for some reason it's pushed away from equilibrium or has enough momentum to pass that equilibrium point, the marble's weight will then lead to another net force that will bring it back. And that is called the restoring force. So the net force that you see here and here, all right, these are restoring forces. So when the marble is released, it does not stop at the bottom of the bowl. It continues to roll up and down each side of the bowl, moving through the equilibrium position. And this is due to its momentum and its inertia. All right. So eventually, when you first actually, let's start with the beginning. When we initially release the ball, the restoring force pulls it back toward the bottom of the bowl, the equilibrium position. But when it reaches the equilibrium position here, it has enough inertia to continue moving up the side of the bowl. But once it starts on the right side of the bowl, the restoring force is now pushing it back toward the center. And it will continue to do this up and down and back and forth in what we call an oscillatory motion. So this repetitive movement is called oscillation. Now, any oscillation is characterized by period and frequency. So for an oscillation, the time to complete one full cycle is called the period. So there and back again is the time that it takes to do that is called the period of the oscillation. Now, the inverse of the period is called the frequency. This is the number of times the thing moves back and forth in a given period of time. And so these two terms, period and frequency, are inverses of one another. So frequency is given as 1 over the period, and period is given as 1 over the frequency. The units of frequency are 1 over a second, or what we call a hertz, named after the famous German physicist Joe Hertz. So QuickCheck 14.1. A mass oscillates on a horizontal spring with a period of 2 seconds. What is the frequency? Well, we know that frequency equals 1 over the period, and therefore 1 over 2 seconds is going to give me a frequency of 0.50 hertz, which obviously you can see here. Okay, and so this spring is moving back and forth horizontally here, and it takes 2 full seconds to go there and back again. That means it only takes half of that time, or 1 second, to go there. Okay, but the frequency is 1 over 2, or 0.50 hertz. A mass oscillates on a horizontal spring with a period of 2 seconds. So same scenario here. If the mass is pulled to the right and then released, how long will it take for the mass to reach the leftmost point of its motion? Well, because the period, the time to go there and back again, is 2 seconds, then to go from the right to the leftmost point will take half of the period. And so therefore, choice A, or 1 second, will be the answer. All right. 14.3. A typical earthquake produces vertical oscillations of the earth. Suppose a particular quake oscillates the ground at a frequency of 0.15 hertz. As the earth moves up and down, what time elapses between the highest point and the lowest point? Well, we know that frequency is equal to 1 over the period, and so period is going to equal, in this case, 1 over the frequency. That's going to give us about 6.6666, or whoops, 7 seconds. However, that's not the answer, because we're going from the highest point to the lowest point, and so that's only half of an oscillation, and half of 6.66666 is 3.3333 seconds. All right, and so there is our answer here. Some common units of frequency that you may have seen in your wanderings. 1 kilohertz, these are frequencies of radio waves. AM radio is given in thousands of hertz, or 1 kilohertz. Megahertz is the frequency of an FM radio station, and gigahertz, all right, these are the frequencies of the radio waves that we use to transmit cell signals. So when your cell phone gets a phone call, it's a gigahertz. All right, all the big networks these days are advertising 5 gigahertz of whatever they're advertising. Okay, now the period of 1 kilohertz is a millisecond. The period of 1 megahertz is a microsecond, and the period of a gigahertz is a nanosecond. All right, so let's try an example problem. An FM radio station broadcasts an oscillating radio wave at a frequency of 100 megahertz. What is the period of the oscillation? Well, this is a fairly straightforward problem. The period is equal to 1 over the frequency. Therefore, 1 over 1 times 10 to the 8th hertz gives us 1.0 times 10 to the negative 8th seconds. All right, and that is on the order of magnitude of 10 nanoseconds. Okay, 10 nanoseconds. Now, when you examine oscillatory motion, for crying out loud, when you examine oscillatory motion, when you go to graph this, you'll feel or find that it takes the form of a cosine function. All right, we'll start with our marble in the bowl example here. If we start on the right-hand side, so we've got a positive position from the equilibrium point, of course, is right in the middle of the bowl. So the right side is going to be the positive position, which you can see at the top of the graph, and the left side will be the negative position, which you can see at the bottom of the graph. So the initial starting point is here. Okay. Now, as the marble rolls down the bowl and to the equilibrium position, its position graph will look like this, and will start or end here at the equilibrium position. But the marble will continue to roll up the other side of the bowl, and so by the time it reaches its uppermost point on the left-hand side, we're at this position here. But immediately the restoring force will then draw it back downward. It'll again cross over the equilibrium point, as we do here, and eventually reach the original point back on the right-hand side of the screen. And hopefully you recognize this curve as a cosine curve. Any graph or function that has the form of a sine or a cosine function is called sinusoidal. All right, you should know that from math. And a sinusoidal oscillation is called simple harmonic motion. So the type of function that describes simple harmonic motion, of course, is choice D, sinusoidal. All right, a couple of examples, just very briefly. You can come back and read these on your own, but examples of oscillating systems, a mass on a spring like we used in a couple of those QuickCheck questions, moving back and forth along a horizontal path. A pendulum oscillates as it swings back and forth. But in biology, for example, we can use oscillations in our tympanic membrane, our eardrum. All right, when a sound goes down the auditory canal, it causes the membrane between the inner ear on one side and the middle ear on the the outer and the middle ear. It causes the tympanic membrane or the eardrum to vibrate. That causes some bones to vibrate, which eventually transfers it to the cochlea, which is an organ designed to send nerve signals to the brain, receiving sound. When you walk, you also can model the motion of your legs using pendulum motion. And so therefore, if you're walking at a constant pace, you are using oscillatory motion in order to do that. Okay, I know I went through that very quickly. This is my second attempt at this video. The first one was too long, so I've kind of tried to cut it back a little bit. Again, any questions, please let me know. There is no homework for tonight. Have a great day, fellas.